In this lesson, we are going to shift our thinking a bit, and instead of talking about discrete random variables, we're going to talk about continuous random variables. So first, recall that a continuous random variable is one for which the outcomes can be any value in an interval or collection of intervals. So, although in practice all measurements are rounded. So, for example, things like heights, weights, etc. Those types of things are continuous random variables. So in the discrete case, a probability density function was given as a table. In this case, this probability density function is a curve such that the area under the curve over an interval, and that interval usually is all possible values, equals the probability that x is in that interval. In other words, the probability that x is between the values of a and b is the area under this curve over the interval between a and b. And the area under the curve for the entire range of possible values must equal 1. That's kind of similar to the values in your table leading to total to 1. So, for example, a common probability density function is something called the normal distribution. And its equation is ugly, gross, and complicated, so I'm not going to write it down because you don't have to know it. But it's centered around its mean mu and is this sort of symmetric bell curve type thing. So there's mu. And the total area under that curve from minus infinity to infinity is 1. So kicker there is that total area under curve is equal to 1. And the second thing is that if I have a value a and a value b, and I find that area, the area under the curve from a to b is the probability that x is in between a, so x is bigger than or equal to a, but less than or equal to b. So just FYI, this notation that I just used, that is how you mathematically write between. Notice how a is the smallest number, and it's the one that's so not being eaten by the alligator thing, and b is the biggest number, and all the alligators eat towards it. I know they're inequality symbols, but if you've heard of the alligator analogy, it is a little bit helpful. So the first example of a probability density function we're going to talk about is the simplest kind, and that simplest kind is called a uniform random variable. This is a function that is a flat line, as in horizontal, that covers the interval of possible values for x. If the range of the uniform value is from a to b, then the base of the rectangle is b minus a and its height is something. I think it helps to have a picture here. So between a and b, our probability density function is equal to something that's non-zero. And outside of there, equal to 0, so flat curve. And a to b encompasses all of our possible values. And it has some unknown height. I'm going to call that height x. Now, first of all, the question is how far is it from a to b? We'll just pretend for a second that a was 1 and b was 7. How far is it from 1 to 7? Hopefully you all said it's 6. Notice you can find that by doing 7 minus 1. So distance from a to b is b minus a. And we know that the total area under the curve is equal to 1. Because that encompasses all of the possible values between a and b. Now that's a rectangle. Its base is b minus a, its height is x. Solving that for x, we see x is equal to 1 divided by b minus a. here's an example of a uniform random variable. So suppose that x is a uniform random variable where x is between 0 and 10. For example, we could say that x is saying the wait time for a bus is between 0 and 10 minutes with a uniform probability distribution. Draw a picture of each scenario and find the probability. So what's the probability that x is between 0 and 3? So our p probability distribution function goes from 0 to 10. And because this rectangle must have area 1, that means the height has to be a tenth. Okay, if this is 5, 1, 2, 3, 4, roughly. So we care about the probability that x is between 0 and 3. Well, that's this part of the curve, which is also a rectangle. Base is 3 there. So the probability that x is between 0 and 3 is equal to the area of that shaded thing, which is 3 times a tenth, or 3/10, or 0.3. So there's a 30% chance you're going to wait between 0 and 3 minutes for that bus. Okay, what's the probability that x will be between 4 and 5? Well, same curve. We still go from 0 to 10. We still have a height of 1/10. Obviously not drawn to scale. Now we just care about between 4 and 5. So the probability that x is in between 4 on the bottom and 5 on the top, well, that's the base of that rectangle is 1, height is 1/10. So the probability wait between 4 and 5 minutes is 1/10, or 0.1. And finally, what is the probability that x will be greater than 5? All right, so same picture, up to 10, height a tenth, 5's in the middle. Okay. Well, probability x is bigger than 5 is meaning that you're waiting between 5 and 10 minutes. Once again, a rectangle, its base is 5, height is 1/10. This comes out to be a half, or 0.5. So that's just to get you to understand the basic idea that these probability density functions have a total area underneath them of 1 when you consider the possible range of values of x. Although uniform variables are not nearly as common, so we're going to move on to more common things now. Before we start this lesson, I want to note that you are going to need a z-table for this lesson. So that was given to you in the same place as your notes. So make sure you take that out and are looking at this z-table, which your book calls table A.1. The most commonly encountered type of continuous random variable is the normal random variable, which has a bell-shaped probability density curve called a normal curve. Any normal random variable is completely characterized by 2 values, and you characterize it by specifying values for its mean, and the notation for that is mu, and its spread, which is called the standard deviation. Notation for that is sigma. Now these curves have some special properties, and we're going to talk about those properties now. So the first thing is that the normal curve is symmetric, and it's bell-shaped. And one should also mention that it's symmetric about the mean. Mu, as in the mean mu is the middle value at the peak. Just a note, not every symmetric bell-shaped curve is a normal curve. There are examples of curves that are symmetric and are bell-shaped but just aren't normal. Now the next thing is the probability that x is less than or equal to the mean is equal to the probability that x is bigger than or equal to the mean. And if you think about it, it's pretty obvious what this has to be. We have a bell-shaped curve centered at the mean. That mean divides this into half. My picture is a beautiful symmetric curve. So the area from mu down has to be 0.5. And the area from mu up has to also be 0.5. So both of these will be 0.5. So this means the probability that a measurement is less than the mean is equal to the probability that a measurement is greater than the mean. The probability that x is less than or equal to mu minus some number is equal to the probability that x is bigger than mu plus that number. And so that's a little bit harder to visualize, but here we go. We have our normal curve. This is our mean mu. Over here is mu plus some value d. Over here is mu minus the same value d. And the thing to note is that obviously this distance is equal to that distance. So the probability that your mean mu, your x is less than mu minus d, that's this area. The probability that x is greater than mu plus d, well, that's this area. And assuming my curve that I drew actually was really symmetric, those two things should be equal. So this means that the probability that x is more than d units above the mean is equal to the probability that x is more than d units below the mean. But the picture is the most important thing. And finally, the empirical rule holds. So this first thing is like saying, what's the chances that x is within plus or minus 1 standard deviation? We learned that that was 68% of all data values, which corresponds to an area under the curve of 0.68. Being 2 standard deviations away, we learned that that was 95% of all possible values. This is area 0.95. And being 3 standard deviations away would have area 0.997. And also note one more thing. The probability that, say, x equals some specific number k. So there's your bell-shaped curve. Suppose this is your k value. We talked about very briefly in the first lesson that you cannot find exact probabilities for continuous random variables, and here's why. The probability that x equals k is the area of this line. But that line has height and no width. So by definition, this is equal to 0. So technically speaking, you can't find the probability that your height is equal to exactly 6 feet. You can find the probability that your height is in between 5.99 feet and 6.01 feet, for example. But you can't find 6 feet exactly because of the whole area of a line being 0 thing. Now here are some common relationships that we're going to use. One consequence of those lines having 0 area is it means the or equal to's are not so important anymore. So here we go. Probability that x is bigger than a. So probability that, that's this shaded part. Well, that's equal to 1 minus all of this stuff from the complement rule. So 1 minus the probability that x is less than or equal to a. And just like the binomial random variable stuff, where we had to have probabilities in the less than or equal to CDF form, the same thing is true with normal random variables. So you're going to use this complementing rule a lot. And just one more time, note that the or equal to business, it doesn't matter if this said equal to or if or not. This could have an or equal to, or it could not. It doesn't change this formula. The probability that x is in between a and b. So some pictures will be helpful here. Well, you could find the area from b on down, but that's going to get some extra. So you take away the probability from a on down, and that in turn gives you this middle thing. So here's that summary. Probability that x is less than or equal to b, and the or equal to really isn't important. So that tells you all of this area. But that tail is extra and you want to take it away. So you minus the probability that x is less than or equal to a. And the thing to notice here is, I know it's weird, but this sign did actually change there. If you think about the picture, it should make sense. And this one we discussed, it's pretty easy to see. The probability that x is bigger than mu plus d is the same thing as the probability that x is less than mu minus d. And as before, it doesn't matter if I have equals to here or not, it's the same thing. So next we're going to use that z-table to find probabilities for a normal random variable. So a standard normal random variable, this is once we've used these z-scores and standardized things, remember that took our mean to 0 and then counted points relative to the mean in standard deviations. And so the sigma in that case was equal to 1. When we convert values for any normal random variable distribution to z-scores, we're converting the random variable we care about to a standard normal. And then you can use this table in Appendix A1 to find the probability that some value z is less than or equal to z star. Okay, and z star is a specific value that we're looking at. The probability z is less than or equal to, say, 3, for example. And recall that the way we found a z-score, we took our value minus our mean divided by the standard deviation, which is the same thing in this case as our x value we care about minus mu over sigma. So first let's review that and find some z-scores. So z is equal to x minus mu over sigma, which is 4 minus 10 over 6, which comes out to be negative 6 over 6, or negative 1. Here our z is 1 minus 1 over 1, 0 over 1. The z value comes out to be 0. For each value of z star, find the cumulative probability that z is less than or equal to this value. So draw a picture and explain what it means. So we want to find the probability that z is less than or equal to 0. Well, 0 is the mean in this standard normal. And if you look this up in the table, you'll find that this is equal to 0.5. So that one's sort of silly, you don't even need the table. Probability that z is less than or equal to 0.35. Well, first let's draw the picture. Mean 0. Oh, that was terrible symmetric thing. Call that 0.35. We're looking for this area. Now, your z-table has two sides. One says standard normal probabilities for z less than or equal to 0 at the top, and one says for z bigger than or equal to 0. So how you find the value corresponding to this value of z is you look in the z bigger than 0 category, and in that table, the first thing that says z, if you go down, that tells you the tenths place, so go down to where it says 0.3, and then as you go to the right, go over to the 0.05, and that gives you the probability that you're less than 3.5. You should get 0.6368. And notice at the top of that page there's a picture that even shows you that what this thing is doing is finding the area from Z down to the left. That's the thing given in the table. Okay, let's do another one, a negative one. Probability that Z is less than or equal to negative 0.35. Okay, so negative 0.35 is over here. We're looking for this area. And I'll use the table and I'll tell you how you could have used a complement to find this out. So we go to the negative Z side and find the same way. Find negative 0.3 and then go over to 0.05. This is going to be 0.3632. Okay, now one thing you could notice is that this area is the same as this area. So therefore, another way to find the answer to part C is you could have done 1 minus 0.6368. You could have used complementing. That's also fine if you see it, not a problem. But what I was trying to get at there was how you use the Z table to find probabilities. Now that we can do that, let's talk about how to apply this to an actual situation. So in this example, we have weights given by the variable x of men in a certain age group, and these weights have a normal distribution with mean mu is 180 and a standard deviation of sigma equals 20. Find each of the following. Probability that x is less than or equal to 200. Okay, so what's the probability that somebody weighs less than 200 pounds? So the first thing you should do is standardize that value, get a z. And we're standardizing this 200. So z is equal to x, which is 200, minus sigma, which is 180, over 20. So that's z is equal to 1. So probability that x is less than or equal to 200 is equal to the probability that the standard normal variable z is less than or equal to 1. And then look at your table. So you're looking for 1.0, and that should correspond to a probability of 0.8413. Notice what that's finding is this. I'll give you another reason to believe that's about right. So you're at 1 standard deviation away. You know from your empirical rule, and we're looking for this area. Your empirical rule tells you that the area plus or minus 1 standard deviation away is about 0.68 inside there. And that leaves 0.16 in either tail, approximately. Notice that 0.16 plus 0.68 is awfully close to 0.8413. So that's another way for you to believe that this is the right number. Okay, let's do another. Probability that x is less than or equal to 165. So first standardize, get the z value. 165 minus 180 over 20. That comes out to be negative 0.75. So the probability that x is less than or equal to 165 is equal to the probability that z is less than or equal to negative 0.75. And then go to your table and look up the negative 0.75's corresponding probability. And you should end up with 0.2266. So the probability that somebody weighs less than 165 pounds in this age group is just 0.2266. And then for part C, because your table goes the other direction as in the inequality, you have to flip using the complement. Have flip. This is 1 minus probability x is less than or equal to 165, which is the complement of the event in part B. So 1 minus 0.2266, which comes out to be 0.7734. So try to keep your work organized, like show me your z stuff and then find your probabilities, and just try to keep it nice and neat and show all of your steps like this. So suppose the yearly rainfall totals for a city in Northern California follow a normal distribution with a mean of 18 inches, so mu equals 18, and a standard deviation of 6, so sigma equals 6. For a randomly selected year, what is the probability that a total rainfall will be in each of the following intervals? So greater than 30. So what's the probability that the amount of rainfall x is bigger than or equal to 30? Well, the first thing you should say is that, well, my table's not going to go that way, so let's make this 1 minus px less than or equal to 30 instead, and then we'll work on that. We'll find probability x less than or equal to 30 to start. So get the z value. Our x value is 30. Minus our mean of 18 divided by 6 gives us a nice old z value of 2. So the probability that x is less than or equal to 30 is equal to the probability that z is less than or equal to 2. And from your table, you should get 0.99, oops, that's wrong, 0.9772. So finally, that wasn't what we were after actually. The probability that x is bigger than or equal to 30, so more than 30 inches, is 1 minus that 0.9772, or 0.0228. So it's quite unlikely for this California town to have a rainfall greater than 30 inches. Okay, how about between 15 and 21? It's the probability that x is in between 15 and 21. So let's start by standardizing those values. Our first z, x minus mu over sigma, so 15 minus 18 over 6. That comes out to be negative 0.5. And the second z is 21 minus 18 over 6, which comes out to be positive 0.5. So this is equal to the probability that z is in between negative 0.5 and positive 0.5. Now remember that to do this one, thanks for your picture, negative a half, positive a half, gotta find the area from a half down, which is probability that z is less than or equal to 0.5 minus probability that z is less than or equal to negative 0.5. So that first one from your table is 0.6915. Second is 0.3085. Comes out to be 0.383. Heights for college women are normally distributed with mean of 65 inches and a standard deviation of 2.7. Find the proportion of college women whose heights fall into the following ranges, between 60 and 70. So the probability that x is bigger than or equal to 60, but less than or equal to 70. So let's start by finding those z-scores. So if x is equal to 60, our z is going to equal 60 minus 65 all over 2.7, which is about negative 1.85. And if x is 70, our z value is 70 minus 65 over 2.7, which comes out to be approximately 1.85. So the probability we were looking for is equal to the probability that z is in between negative 1.85 and positive 1.85. And once again, you do the area from 1.85 down, z less than or equal to 1.85, minus the area from negative 1.85 down. And that gives you the area in the middle. So this is 0.9678 minus 0.0322, which comes out to be 0.9356. And based on previous knowledge, you should kind of believe that answer. So 1.85 standard deviations away is awfully close to 2 standard deviations away. This is the probability you're between 1.85 standard deviations above or below, which is a little bit under 95%. So it's kind of confirming or consistent with the empirical rule that you know. Part B is related to Part A, so knowing Part A will be quite helpful. So what's the proportion of college women whose heights are less than 60 or greater than 70? Well, it knows that those are two mutually exclusive events, so we can find the first probability plus the second. And also notice that in Part A, we found the part between 60 and 70, we found that area. In this problem, we're looking for the other area, the area in those two tails. So this will be 1 minus the answer to A, or 1 minus 0.9356, which comes out to be 0.0644. Okay, so you'll have to now take some time to practice those normal random variables and practice using that z-table to get probabilities. And then to end the lesson, let's do an example of a binomial random variable. So suppose that I have a treatment for some hypothetical disease, and if I apply this treatment to a random patient, the probability that they recover is 0.8. I'm going to apply this treatment to 4 patients. So if x is the number of patients who recover, x is a binomial random variable. How do you know this, and what must we assume about our trials? And what are the possible values for x? And then what are n and what are p? Okay, so first of all, we know this is binomial because there are 2 outcomes. That's where the whole bi part comes from. Success, which is recovery, or no recovery. What must we assume about our trials? The trials must be independent. The possible x values, as in x is the number of patients who recover out of 4. You could have 0, 1, 2, 3, or 4 people recovering. The n is 4. The probability of success is 0.8. First of all, what is the mean of this binomial random variable? And what does it mean in the context of this situation? So our mean mu is e of x, which is given by np. Now n is 4, p is 0.8, which comes out to be 3.2. Okay, so over many, I don't want to say trials, we expect 3.2 of every 4 patients to recover. On average. Okay, what is the probability that exactly 2 individuals recover? So remember that our formula was Px equals k was n factorial over k factorial n minus k factorial p to the k 1 minus p to the n minus k. So we're looking for the probability that our x value is equal to 2. Remember our n is 4, so we have 4 factorial over 2 factorial times 2 factorial. Our success probability is 0.8 to the 2, because we have 2 successes, which means we have 2 failures as well. Okay, so simplify those factorials. 4, 3, 2, 1, 2, 1, 2, 1, 0.8 to the second, and then 0.2 to the second. Okay, well, some of those numbers are going to cancel. 2, 1 cancels that 2, 1. And we could say 4 divided by 2 makes 2, giving us 6 as the coefficient. 6 times 0.8 squared times 0.2 squared, which gives us a probability of 0.1536. So the probability that exactly 2 patients recover is 0.1536.